angular integration which comes out to be 1/3, the total pressure due to atoms of all speed ranges from 0 to infinity is given by P times V is 1/3, which is due to the angular integration 0 to 2 pi d phi 0 to pi by 2 cos square theta sin theta d theta divided by 2 pi. This will comes about to this will be this will come about to be 1/3 1/3 m 0 to infinity v square into d n. The average of the square of atomic speed, which is known as the root mean square speed, is defined to be v square average is 1 by n 0 to infinity v square times d n. Okay. This is known as the root mean square velocity, which is defined as the average of the square of the velocity. So, that we have P v equal to n capital M, which is the total number of atoms or molecules, times mass m divided by 3 into root mean square velocity. This is the famous equation of the kinetic theory of perfect or ideal gases. Now, let me write down this equation in other form also. Now, small m into capital M equal to small n m into capital N equal to capital M, which is the mass of the gas. So, in terms of this, which is nothing but the m by v, which will give you the rho, where rho is the density of gas. Then the above equation can be rewritten in terms of P equal to 1/3 rho v square average. So, where rho is the density of the gas, or equal to 2/3 E, where E is the kinetic energy per unit volume, which is half times root mean square velocity. So, this is another way to write down the equation in the of the kinetic theory of gases. First way is to write down in terms of P v, second way you can write down in terms of P in terms of the density of the gas. Thus, the pressure of a perfect gas is numerically 2/3 of the kinetic energy per unit volume. This equation is called the basic equation of the kinetic theory of gases. In deriving equation 1, we have made no assumptions about the nature of molecular impact against the wall. We have not made any assumptions what is the nature of molecular impact against the wall. Now, let me see what is the mean square velocity of the molecules of a gas. Mean square velocity from that equation 1, we can see it is 3 p by rho, where p is the pressure and rho is the density of the gas. Hence, the root mean square velocity is given by is square root of 3 p by rho. That means, if the density of the gas is large, in that case root mean square velocity will be small. If the density of the gas is very low, root mean square velocity will be very large. Knowing the pressure and the density of a gas, experimentally people have calculated root mean square velocity, and hence C can be calculated. Kinetic interpretation of temperature. Till now I did not talk about what is the concept of temperature, how the concept of temperature has come. Okay. So, let me start it. Let us consider a gram molecule of a gas which occupies a volume V. From equation 1 we can get P v equal to 1/3 m times average values of V square, which is nothing but the root mean square velocity. In the kinetic consideration of a perfect gas, we use the experimental equation of state, which is P v equal to R t. In that case, where R is the gas constant and T is the absolute temperature. If you will compare the equation 4 and 5, what you will see average values of V square, which is the root mean square velocity, which comes out to be 3 R t by m, where R is the universal gas constant, m is the mass of the gas. That means, if R and m are constant, and which is indeed true, then average values of V square is proportional to T, where T is nothing but the temperature, or other way around, V square is proportional to the absolute temperature. This is the kinetic interpretation of temperature. That means, till now we did not know what is temperature. Now we come to know temperature is nothing but it is a measure of the average values of the kinetic energy. Average values of the kinetic energy means how you have got V square by 3. This is because of the isotropicity of momentum in the momentum space, where average values of V x square equal to average values of V y square equal to average values of V z square. That means, in other way around, temperature is nothing but whenever there will be equilibration in the momentum space, that situation is known as is coined as the temperature. Okay. So, according to the kinetic theory, all the molecules should have 0 velocity at the absolute 0 of the temperature. However, this result is not justified as CH2 behaves as an ideal gas before reaching the absolute 0 of temperature, because whenever you approaches the absolute 0 temperature, that times the concept of perfect gas ceases to exist. At very small temperature, there is no gas which can be called as an ideal gas. Only ideal gas, the realization of ideal gas holds good at very large temperature and very low density. So, that is the reason you cannot simply extrapolate that as temperature tends to 0, the velocity tends to 0. So, simply you cannot extrapolate it. Okay. Again, if you will write capital M equal to small m into Na, where Na is the Avogadro number, then the above equation 6 can be written as half Na times m into average values of V square equal to 3 by 2 R T, where R by Na equal to K, where K is the Boltzmann's constant. So, finally, we got the equation half m average values of V square equal to 3 by 2 K T. Thus, the mean kinetic energy of translation of molecules can be regarded as a measure of temperature. However, in that case, the average energy per atom is wholly kinetic energy of translation. Now, the concept of monoatomic gas will play the major role. In case of monoatomic gas, the kinetic energy is purely translation in character, whereas if you will go to the diatomic gases, although the diatomic atoms not interacting with each other, but it can rotate, it can vibrate with respect to the axis passing through its equilibrium position. So, that is the reason the average values of kinetic energy, whether it will be the 3 by 2 k T or other values, it depends on whether it is a monoatomic gas or whether it is a diatomic gas, whether it is a triatomic gas. In our cases, since we have started the kinetic theory for the monoatomic gas have only translational kinetic energy, it cannot have rotational or vibrational kinetic energy, because it does not have those degrees of freedom. So, this is the only kinetic energy that a hard spherical atom uninfluenced by its neighbor or field can have. Therefore, we have limited ourselves to a monoatomic gas only. Diatomic and polyatomic molecules can also rotate and vibrate and may therefore be expected to have energies of rotation and vibration, even though there are no forces between the interacting molecules. But till now we will not talk about the kinetic theory of gases for the diatomic or polyatomic gases. In the next part of my lectures, we will confine ourselves only to the monoatomic ideal gases. Okay. Whenever we used to claim that we are giving a new theory, new microscopic theory, so we have to define, we have to calculate some quantities and tally with the experimental result. So, let us calculate the internal energy of a gas of atoms using the kinetic theory of gases. In kinetic theory, it is assumed that atoms behave as non-interacting particles, as we have told you that there is no interactions among atoms, only interaction are occurring between the collision of atoms with the walls of the gas. So, the potential energy of their interaction may be neglected. The only form of energy these particles may possess is the translational kinetic energy. They may not possess, for example, rotational or vibrational degrees of freedom. However, in case of monoatomic gas, there are no rotational and vibrational degrees of freedom. So, there is no kinetic energy which are associated with the rotation or vibration. Okay. So, therefore, the internal energy of the ideal monoatomic gas is the sum of kinetic energies of all its atoms. That means, U is summed over half m v j square, where j runs from all atoms in the gas. Okay. So, I can take outside, so which is nothing but the n times half m average values of v square. So, using the above equation to replace the kinetic energy, we obtained a calculated expression for the internal energy of a monoatomic ideal gas, which is U equal to 3 by 2 n R T, where n is the number of moles, R is the universal gas constant, T is the temperature. So, the internal energy of ideal monoatomic gas calculated from the kinetic theory of gases is proportional to the thermodynamic temperature only, and this agrees with the experimental result. However, we have already seen from the thermodynamics that internal energy depends only on temperature, but we do not know how to get it. So, this is the beautiful aspect of the kinetic theory, through which we have started from the microscopic point of view, which deals with the constituent of the system, and finally, we have landed up with a beautiful expression which is which shows that internal energy does depend only on temperature only. In the kinetic theory of gases, the concept of temperature is primarily a foreign element, since in fact, the individual atoms are characterized by the speed only, but it is suggestive that we should define the ideal gas temperature in terms of the mean kinetic energy. So, last but the least, I want to mention what is the beauty of the kinetic theory of gases. What are the most important points which should be mentioned in this lecture. Those above results, whatever we have derived, has been derived from the laws of physics and statistics, rather than being formulated from experimental data, which has been done in the theory of thermodynamics. But in case of kinetic theory of gases, we have derived it from the laws of physics and statistics, and from the first principle of calculation, and it has come automatically that the expression of the internal energy. Okay. So, next we want to convince ourselves that whatever we have derived it, whether it can reproduce the known laws which is known to us since 400 to 500 years ago. So, let us derive those laws from the kinetic theory of gases. Okay. Some fundamental law of ideal of perfect gas can be deducted from the basic equation which we have already derived. First, Boyle's and Charles' law. We consider a gram mole of gas at absolute temperature T occupying volume V. So, that we have P v equal to 1/3 mn V square average. According to the kinetic theory, the mean square velocity of the gas is proportional to the absolute temperature. So, V square average proportional to T, where equal to alpha times T, where alpha is a constant. So, the above equation we see that P v is 1/3 m n into alpha into T. So, at a given temperature P v equal to constant, which is nothing but the Boyle's law. As we know, what does it mean by Boyle's law? For a fixed amount of ideal gas kept at fixed temperature, P pressure and volume are inversely proportional to each other, while one increases other decreases. This is Boyle's law. The Boyle's law is based on the empirical observation since 100 years, but from the kinetic theory of gases we have got this law automatically. We did not take any assumptions, we did not we did not analyze any experimental result, it has come automatically from the kinetic theory of gases. That is the beauty of any microscopic theory. Again from the same equation, if you will rewrite in other way, V is proportional to T when P is held constant, which is nothing but the Charles law. So, what is Charles law? At constant pressure, the volume of a given mass of an ideal gas increases or decreases by the same factor as its temperature on the absolute temperature scale. So, that means the gas expands as temperature increases, as gas shrinks as the temperature decreases. So, this is Charles law, and again the emphasis is given to the kinetic theory of gases. The Charles law, which is based on the empirical observation since 100 years, but from the kinetic theory of gases this Charles law has come automatically. That is the beauty of the kinetic theory of gases. We have already told how Charles law, Boyle's law could come out automatically from the kinetic theory of gases. Let me tell how Avogadro laws could come automatically from the kinetic theory of gases. Let me see how it can be derived automatically. Let us see, let the two ideal gases, gas 1 and gas 2, have the equal volume at the same temperature and pressure. When the two gases are at the same pressure, then we have from the kinetic theory that they should have the same kinetic energy, because we know that since P pressure, volume and other pressure and volume remains the same. So, that means the average kinetic energy of the gas 1 should match with the average kinetic energy of the gas 2. So, that means P v equal to 1/3 m 1 n 1 v 1 square average equal to 1/3 m 2 n 2 v square average. When the two gases are at the same temperature, let us say their temperature is also same. So, that means their average kinetic energy of the gas 1 and gas 2 should be the same, because temperature is a measure of the average kinetic energy. Since we are saying temperature remains the same, if the temperature held constant, then the average kinetic energy of the gases 1 equal to should be the same as the average kinetic energy of the gas 2. So, that means the average kinetic energy of molecule of both the gases are the same. So, that means half m 1 v 1 square average equal to half m 2 v 2 square average. If you will combine these two equations, we will get n 1 equal to n 2. That means number of atoms or molecule in gas 1 should be equal to the number of atoms or molecule in the gas 2, which is nothing but the famous Avogadro's laws. Okay. The beauty, again it should be emphasized, beauty of this derivation is that it is not based on the experimental data since years and years. It has come automatically from a microscopic theory. In our case, it is the kinetic theory of gases. Thus, equal volume of all gases under the same conditions of temperature and pressure have the same number of molecules, which is the celebrated Avogadro's law. Now, next go to the laws of partial pressure, Dalton's laws of partial pressure. So, as we have already told you in the first transparency, as we have already told you in the very first transparency, that gases are infinitely miscible. That means, gases mix in any proportion such as in air, a mixture of gases. So, when you will mix the two gases, what will be the total pressure? So, let me start. Let there be a mixture of number of gases of densities rho 1, rho 2 and of mean square velocities v 1 square, v 2 square in the same volume v. That means, in a given volume you have taken two gases and you mix them. Then the total pressure exerted by the mixture is given by P pressure, since it is a scalar quantity. So, the pressure could be added together. So, pressure due to the gas 1 will be half 1/3 rho 1 V 1 square average, where rho 1 is the density of the gas 1, V 1 square average is the mean square velocity of the gas 1, plus 1/3 rho 2 V 2 square. This is due to the gas 2, where rho 2 is the density of gas 2 and V 2 square is the average velocity of the gas 2, which is nothing but the P 1 plus P 2, which is nothing but the pressure exerted by the gas 1 plus pressure exerted by the gas 2 and the pressure exerted by the other gases. So, where P 1, P 2 are the partial pressure exerted by the different components of the mixture occupying the same volume V. So, thus the pressure exerted by the mixture as a whole is equal to the sum of the pressures exerted separately by the individual components. So, that means, if there are n component gases are there, so that means the pressure of the n component gas should equal to the sum of the pressure by the individual components. That means, P should be summed over P I, where I ranges from 1 to n, where n is the number of components. So, this is nothing but the famous Dalton's law of partial pressure. Again the emphasis goes back to the kinetic theory. It has come, this Dalton's law of pressure has come automatically from the kinetic theory of gases without any experimental data. Graham's law of diffusion, this is a very famous law of diffusion. What is it? So, now let us take two gases, gas 1 and gas 2, and obviously since there are two different gases, their root mean square velocities will be different. Let us take the root mean square velocities of the gas 1 and gas 2 are V 1 and V 2 respectively, and their densities are also rho 1 and rho 2 respectively. Then we know from this relation of relation of root mean square velocity, which is nothing but the square root of 3 p by rho, we can write down the root mean square velocity for the two gases separately. First one is V 1 equal to root over 3 p by rho 1, where rho 1 is the density of the gas 1, and velocity root mean square velocity V 2 for the gas 2 is 3 p by rho 2, where rho 2 is the density of the gas 2. Now, if I will take this ratio, what I will get V 1 by V 2 is equal to square root of rho 2 by rho 1. So, that means root mean square velocity is proportional to 1 by square root, or it is inversely proportional to the square root over their density. That means, if the density of the gases are large, their root mean square velocity will be very small. If the density are very small, then the root mean square velocity will be very large. So, using the density dependent root mean square velocity, the gas diffuse accordingly. Thus, the rate of diffusion of a gas is inversely proportional to the square root of the density. This is famous Graham's law of diffusion of gases. Using this Graham's law of diffusion of gases, we can see in our nature why one gas diffuses more rapidly compared to the other gas, because of their origin of the root mean square velocity depends on their density inversely. We can calculate some various constant using the kinetic theory of gases. However, we know the values of constant earlier because of some experimental data, but the values of some constant will come beautifully from the kinetic theory of gases. Those are very famous constants. First is Avogadro number, the number of atoms or molecules in 1 gram mole of gas. So, if m is the mass of a molecule, then the molecular weight is capital M equal to small m into number of particles, which could be the Avogadro number. So, Avogadro number Na equal to molecular weight by the mass of a molecule. For hydrogen gas, m equal to 2 molecular weight and small m mass of a hydrogen molecule is 3.32 into 10 to the minus 24 gram. If you will put there, then Avogadro number will comes out to be 2 by 3.32 into 10 to the minus 24 is equal to 6.024 into 10 to the power 23 number of particles per mole. So, this is the Avogadro number which comes out to automatically from this. Second, universal gas constant, which is a very famous constant, which is known as the universal gas constant R. For 1 gram mole gas, we have the relation P v equal to R T, because N has become equal to 1. So, R equal to P v by T. Let us calculate at normal pressure and temperature NTP. We know at normal pressure P is 76 centimeter of mercury. So, which is nothing but in terms of calculating the CGS units 76 into 13.6 into 78 dynes per centimeter square, which is equal to 1.02 into 10 to the power 15 Newton per meter square. Volume, as we know, in the normal pressure and temperature 1 mole gas occupy 22.4 liter volume. So, V is 22.4 into 10 to the power 3 cc. Temperature is 273 degree Kelvin. So, if you will substitute all these values in the equation R equal to P v by T, we will R will comes out to be 8.31 joule per mole Kelvin. In terms of calorie, it will comes out about 1.99 calorie per mole degree Kelvin. First, last but the least, Boltzmann's constant, which is a very fundamental in the sense this Boltzmann constant is the first constant which connects to the microscopic world through the famous relation of entropy equal to entropy is proportional to the logarithmic of the number of accessible microstates, and proportionality constant is Boltzmann's constant. This relation is fundamental in the sense this is the first relation which connects the macroscopic world, means thermodynamics, to the microscopic world, the number of possible microstates through the Boltzmann's constant. You can calculate Boltzmann's constant through this beautiful relation which we have already come across in the kinetic theory of gases earlier. This here, let me show you the earlier transparency. This R by A equal to K, where K is the Boltzmann's constant. So, K equal to R by Na, Na is the number Avogadro number, R if you will substitute the values of R and Na, then K will comes out to be 1.38 into 10 to the power 16 arc per degree Kelvin. In terms of joule, it will comes out to be 1.38 into 10 to the minus 23 joule per Kelvin.